All right, welcome back. It's time to start on our next concept. This is going to be one of our biggest concepts that we go over in physics, and it is forces. All right, so forces are everywhere, and hopefully, in the last couple of days, with all of our stations activities, you have already begun to be introduced to these or reintroduced to different forces and what they mean. All right, how they act and how they affect things. All right, so we're going to be just talking about what a force is. All right, so if we have an object, you saw in one of the stations yesterday, you were introduced or reintroduced to Newton's first law of motion. All right, just to recap, Newton's first law of motion says an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by an unbalanced force. All right, so what that just means is that an object is either going to stay still or it is going to stay in its constant state of motion unless something acts on it. So unless something either pushes it or pulls it or does something of that sort. All right, so we refer to those pushes and pulls as forces. All right, there are a ton of different forces. We're just going to touch on the basics. All right, but all of those forces are signified with this capital F. All right, so the definition that we give to a force is just an action that is exerted on an object that may, all right, I want you to highlight that may change the object's motion. All right, we're going to dive into that in just a second. All right, but yesterday you were also introduced to the unit that we use for force, and it is the Newton. All right, that's just a capital N. All right, so obviously that comes from Isaac Newton. We're going to be going into depth into his 3 laws of motion. Like, he was pretty big whenever it came to this kind of stuff. All right, so if we look at this unit, a Newton is just a capital N. It's one single letter. All right, so if we go back to the very beginning of our course, we talked about base units, and then we talked about derived units. Okay, so we talked about base units. These were the physics base units, not the base units that we talked about in chemistry. We use 3 base units in CP physics, and that's going to be our kilogram for mass, our second for time, and then a meter for length. All right, those are our 3 base units. Now, whenever we start doing these equations, all right, and combining all of these different what is it? Oh my goodness, where did my brain just go? All of these variables. That's what I was looking for. Whenever we start combining all of these variables mathematically, that's when we end up getting these derived units. All right, so our Newton, even though it's just one single letter, it's not a base unit, it is a derived unit. All right, and here we see the derivation of that unit. All right, so all that statement says, what you're looking at says that 1 Newton of force causes a mass of 1 kilogram to accelerate at 1 meter per second every single second. That's what that means. But we're going to look at it, and just using that derivation of a Newton, we can actually discover Newton's second law of motion. All right, so if we take it piece by piece, all right, we know that Newtons are a measurement of force. Kilograms are a measurement of mass. All right, this little star is just a multiplication sign. And then we know that meters per second squared represents acceleration. So here we have force is equal to mass times acceleration, which is Newton's second law of motion. All right, so as we look at this, because we have mass and acceleration that are giving us force, we know mass is a scalar quantity, but acceleration is a vector quantity, meaning it has both a magnitude and direction. So because acceleration has that direction, force is also going to be a vector quantity. It is a vector quantity, meaning it has both magnitude and a direction. All right, so going back to this, forces can change an object's motion. All right, if you were to look at this in the PowerPoint form, all right, you would see this guy sliding into third base. All right, now as he is sliding, he is not going to keep sliding forever and ever and ever, amen. No, he is eventually going to come to a stop. Now, hopefully you already know that it is friction that's going to cause him to come to a stop. All right, and that friction is a force. All right, so these forces can change the motion of an object, but it doesn't always have to. All right, if we look at this phone, I know that a lot of you have probably never even seen a phone like this in real life, but maybe you've seen it in a movie. All right, so this phone was just left hanging. So this is how we used to put people on hold. We just left the phone right there. All right, so we should know that there is one force that is always working on all objects, and that is the force of gravity. All right, so gravity is pulling this phone straight down. All right, we have gravity working on the phone, pulling it down. But this phone is not going down, 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 down. So we have another force that is working against gravity that's keeping the phone right where it is. All right, and because we see that this is a cord, all right, this cord acts as a spring. We have an elastic force or a spring force. They're one and the same, all right, that is pulling it right back up. Okay, so this phone is, it has forces being exerted on it, but it is not changing that motion. So that tells us that all of these forces can change the motion, but they don't have to. All right, whenever you have these forces that do not change the object's motion, these forces are said to be balanced. All right, these forces are balanced. All right, so there are two different scenarios that you can have balanced forces. And that is just like the phone, we can have an object at rest. Or another way is if an object is already in motion, it's just going to keep going with that same motion. So it's going to have a constant velocity. All right, so those are two different scenarios in which we can have balanced forces. All right, so if we look at this object right here, all right, we're going to draw, you were sort of introduced to free body diagrams in the stations work, but we're really going to dive deep into those later on. All right, so if we draw this as a free body diagram, one thing I always mention here, I use this because I hate it. It's kind of a what not to do. Do you see how these forces are going into the object? We never, ever, 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 ever draw our arrows representing our forces going into the object. We always draw them going out of the object. All right, so our force A is a rightward force. All right, so we're going to draw it coming out of our object, going to the right. And our green one is a leftward force. So we're going to draw it coming out of our object and going to the left. All right, now, as you can see here, all right, they are relatively the same size. So we're going to give them numerical values. All right, because our force A is headed to the right, that's going to be a positive force. All right, and we're just going to say it's a positive 20 Newton force. All right, now for us to be balanced, it has to be equal in magnitude and opposite in direction. So that means that force B is going to be negative 20 newtons. All right, so if we were to combine these, just like we did vectors, all right, negative 20 plus a positive 20 does give us 0. Whenever we combine these, that is something called a net force. All right, it's the same thing as saying the resultant force. So whenever we add our forces together, we get a net force. All right, whenever they cancel out, that means that we have a net force of 0 newtons. And whenever we have a net force of 0 newtons, that tells us that we are balanced. We know that we are either at rest or we're going at a constant velocity. So we know that we also have no acceleration. All right, so whenever we do have objects that are balanced, that have these balance forces, again, they can either be at rest or going at a constant velocity. They are said to be in equilibrium. All right, if you say that word, equilibrium, that sounds like the word equal. And so hopefully you're realizing that. So these forces are balanced because they are equal in magnitude, but opposite in direction. That's what makes them cancel out. All right, so right here, you see the iceberg and you see the Titanic. These objects are not moving. They are stationary. All right, so they're not going up and down. They're not bobbing up and down in the water. All right, so we know that the forces are balanced. Well, we know that our force is always pulling us down is going to be the force of gravity. All right, but they're both in the water. All right, so we saw this in the station where we had the ball floating in the water in the beaker. All right, that was caused by the difference in densities. All right, but that is also a force being exerted called a buoyant force. All right, it is a buoyant force. So that buoyant force is pushing that iceberg and pushing that boat back up. All right, so that's what that F sub B stands for. All right, now this right here is again introducing you, it's kind of bringing back vectors, but it's also starting to introduce you to these free body diagrams. All right here, we have an object that has two different forces being exerted on it. Now, different from this one right here, these were going in opposite directions. This one has two forces that are being exerted on the object going in the same direction. All right, so if we were to draw a free body diagram, we would not draw it like this. We have to go back to whenever we were adding vectors together, and we have to use the tip to tail rule. All right, so we add these to tip to tail, and so we get our resultant force or our net force by doing that. We add them together. All right, so our free body diagram would look like this. That would be our net force. Well, if you look at that, you only have one arrow on one side. There is not an arrow on the other side that is balancing it out. All right, so this is called unbalanced forces. All right, so just like up here, we can have two scenarios if we have balance forces, and that's when an object is at rest or going at a constant velocity. Whenever they are unbalanced, you are going to have some type of acceleration. Now, we have to remember that there are three ways that we can have acceleration. So we can be speeding up, we can slow down, or we can change direction. if we have any of those three things happening, we know that we have acceleration. And if we have acceleration, that tells us that our forces are not balanced. All right, so let's look at this free body diagram again. Again, we're going to redraw this because we do not like the arrows going toward the object. They go out of the object. All right, so our red force is a rightward or a positive 20 Newton force, while our green force is a leftward, so negative 35 Newton force. Well, if we were to combine those, we would get a net force of negative 15 newtons. All right, that negative 15 newtons is not zero. So this is unbalanced. All right, it is unbalanced. So if we have an unbalanced force, we know that we have some acceleration. Our acceleration is not going to be zero. All right, now if we look at these two objects, these two free body diagrams right here, the red, you can tell those arrows are not equal. They're opposite in directions, but they are not equal. So that tells us these are unbalanced forces. These are unbalanced forces. So we know that we have some type of acceleration going on. So we're either speeding up, we're slowing down, or we're changing direction. And we also know that that means that our net force is not going to be zero, and we will not have an acceleration of zero. So we have some net force. This one is going to be some net force in the positive direction, which means that our acceleration will also be going in the positive direction along with that net force. All right, for the green one, we see that those arrows are going in opposite directions, and they're also equal in magnitude. So these are balanced forces, which means that we are either going to be at rest or we're moving at a constant velocity. All right, either one of those. So both of those mean that we do have a net force of zero. And because we're either at rest or going at a constant velocity, we have no acceleration. All right, so these are the things that you have to know for balanced and unbalanced forces. You have to know those. All right, now the last thing that we're going to talk about is the two different categories that all forces can be put into. And those are going to be field forces versus contact forces. All right, hopefully the name, the category that these are in kind of tells you what happens with them, all right, to put them in these different categories. All right, but let's look at them. All right, so the other day whenever we were doing our lab, you saw the balloon. All right, you had the balloon and the pieces of paper. All right, so I told you to rub the balloon either on your hair or on your sweater, but I told you not to actually touch them together. All right, and that was to show that they would be attracted to each other without touching each other. All right, and everybody got it. You said that it was static electricity. All right, so what you were looking at was the electric force field between the balloon and the paper pieces. All right, we also had the station where you had to make the discs float. All right, most of you struggled with that, but some of you got it. You realized right away that we were dealing with magnets. And like electric currents, all right, so electricity has charges. So they have a positive charge and a negative charge. Well, we know that positive and negatives are attracted to each other, while positives and negatives repel each other. Well, magnets don't have charges, they have poles. So you had the north pole of a magnet and the south pole of a magnet. and the North and the South Pole will attract each other, but the North Pole and South Pole of two different magnets will repel each other. All right, so you saw how you did not have to touch the magnets together in order for them to either be attracted or repelled. And that was magnetism. That was a magnetic force. All right, gravity is going to be one of the biggest ones that we come in contact with every single day. All right, our gravity comes from the earth. All right, everything exerts gravity, all right, but Earth is very large, so that's where most of our gravity comes from. All right, but if I am standing 3 stories high, all right, I am not on the surface of the earth, but I'm still feeling the effects of gravity. If I jump out of a plane, I am not on the surface of the earth, but I sure am feeling the effects of Earth's gravitational pull. All right, so that gravitational force is definitely a field force. And then nuclear force is what we talked about last year in chemistry. All right, so we know that we have 3 subatomic particles. All right, we have protons, neutrons, and electrons. All right, so we have the nucleus that contains our positively charged protons and neutral neutrons. And then we have electrons that are outside of that nucleus. And so the electrons are not stuck to the positively charged nucleus, but they are orbiting it. All right, and they are not touching, but they are still feeling the effects of that nuclear force. Those protons are pulling those electrons in, so they are all field forces. All right, the others, I'm going to add to these. The others are contact forces, meaning these have to be in physical contact with each other in order for them to be exerted, in order for that force to be exerted on an object. All right, friction is definitely one of those. So friction happens whenever 2 surfaces come in contact with each other. All right, so sliding, all right, that is friction. All right, another type of friction is air resistance. Air resistance is a force in and of itself. It is a type of friction. All right, so if you have something that's moving through the air, that air is flowing past you, so it's touching you or touching the object. All right, so it's contact. All right, spring force. So we talked about the difference between spring force and tension force yesterday. All right, you have to have a spring on something. You have to have a rope, a cable, a wire on something in order for them to exert their force. All right, and then we have something called a normal force. All right, a normal force is huge. This is whenever something is on a surface. All right, so if you take a book on a table, all right, gravity is pulling that book down, but it's not going down, 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 down. So something has to be working against gravity, and that's the table right there. So the table is exerting a normal force, pushing back up on that book. All right, now because the book is not moving up and down, we know that those two are balanced. All right, but if something is on a surface, on the ground, on the table, on the roof, anything like that, all right, it is going to have a normal force. And the last one that I want to add is something called an applied force. All right, an applied force is just whenever you physically put your hands on something. So if I were to push this book to the right, I would be applying a force. If I pull a table one direction, all right, then I am applying a force. An applied force is not a rope pulling something with a rope or a wire or a cable or a cord or anything like that. An applied force is just whenever I have, like, my hands are pushing or pulling something to make it move or not move. Maybe I'm not strong enough to make it move. All right, but that's the difference between an applied force and a tension and spring force. All right, so I hope that this makes sense. We are going to do a concept builder where you have to recognize the different forces in play. So this should give you a good basis for it. But as always, if you have any questions, just let me know.